So welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Reinhard Genzel, who's come across to us from UC Berkeley. Reinhard did his bachelor's at the University of Freiburg and then a PhD at the University of Bonn. And then he went to the Harvard-Smithsonian Institute in Cambridge, Massachusetts. And then he came across to the West Coast as a Miller Fellow at UC Berkeley. After that, in 1986, he joined the Max Planck Gesellschaft, and he's been at the Max Planck Institute for Extraterrestrial Physics since that time. He's also recently been appointed a full professor at UC Berkeley as well, and that's how we get to have him come across to us today. Reinhard is a recipient of the Albert Einstein Medal, the Shaw Prize, the Crawford Prize, and he's a foreign member of the Royal Society of London. His interests revolve around infrared and submillimeter astronomy, using that to look at the formation and evolution of galaxies. And he's also very interested in tracking the motions, and he's a pioneer in the area of tracking the motions of objects around the Milky Way center, which is what he's going to talk to us about today. So please join me in welcoming Reinhard.
Thank you, Adrian. Right. What is common between SETI and MPE? And that is extraterrestrial. Extraterrestrial, yes. So the institute I'm spending most of my time in, MPE, is one of the 88 institutes of the Max Planck Society for basic research. Wonderful place to be there, and our institute, in fact, in many ways has interest, or had interest, I should say, which SETI Institute had, not so much the extraterrestrial life, but basically exploring the universe around the Earth. The subject of today's talk is one which, to some extent, couldn't have been a topic of a talk 20 years ago. It's really a new field. I could not power up quasars for any length of time at that level. And therefore, you had to find something which is more efficient than fusion. And it turns out that a black hole, while it is black in the sense that there's this event horizon you can't see in or you can't communicate outwards, can generate energy in enormous rates, because when particles, material, rocks, astronauts, or anything else is basically falling into the hole, just before they disappear in the event horizon, they can basically convert a significant fraction of their gravitational energy into heat and therefore radiation. And that turns out to be about a factor of 100 more than fusion. So between 10 and 40% of the rest energy can be converted into radiation. So that was the idea. And of course, now the next question is, how could you prove that? How could you prove the existence of black holes? To do it with quasars seemed hopeless, still seems hopeless nowadays, in the sense of a true physics experiment. Because what you want to do, and let me just say, if you want to prove that such an object like a black hole exists, you would have to measure the gravitational field, or the space-time, down to scales of the event horizon, right? You would have to prove that there's an object there which is so concentrated that it must be a black hole, and for that you want to see that it, in fact, as the theory predicts, has an event horizon. And for surely for quasars, because they were so far away that it's just hopeless to try to make measurements on that kind of a scale. So then Donald Lindenbell and Martin Rees, two of the theoreticians who had been working on the problem in the 1960s, proposed, well, if there are these massive black holes in quasars, maybe they're everywhere. Okay, by then it was already clear that quasars basically were the cores of galaxies. And basically the idea is very much like the solar system. If you think of the sun and the planets orbiting around the sun, now just think mentally that the sun does not shine. you could still prove from the motions of the planets that the sun exists, and you could even measure its mass. And if you measure so that's the idea here. And so Rees and Lindenbell proposed in the galactic center, which is obviously the nearest galactic nucleus by a factor of 100,000 over quasars, and only 26,000 light years away, you could measure emission line width. At the time they thought about hydrogen. You will see that we use nowadays stars now, and so you have to switch on your infrared light eyes or radio eyes or X-ray eyes. And in this picture, in fact, you don't notice it. We have now gone to wavelength of about 2 micrometers, where you can begin to see the inner part of the galaxy here. And there, in fact, is a very concentrated cluster of stars, very dense, about 1 million times denser than the solar neighborhood. And in the center of that, in fact, the radio astronomers indeed find a very compact radio source called Sagittarius A star. So that's sort of the setting in the galactic center. You have a central compact radio source, which might be, so to speak, and in fact, here's a little gallery of the kind of techniques are being used nowadays to chase down black holes in the galactic center, but also elsewhere. You will see a lot of data now from these types of telescopes, which are the biggest ground-based optical and near-infrared telescopes, 10 meter in diameter approximately, and equipped with instrumentation, which we are now been developing over 20 years, which allow you to whether you take a 10 centimeter telescope, a 1 meter telescope, or a 10 meter telescope. So to come to optical diffraction, which for these 10 meter telescopes in the near infrared is about 50 milliarc seconds or so, you have to overcome this blurring of the Earth atmosphere. And that's done with the technique of adaptive optics, where you basically measure what the Earth atmosphere does, and then you correct for it by having a so-called deformable mirror. So this technique now, in fact, has really been sensational and has led to breakthroughs in this kind of technique. Of course, you can bring a telescope out in space, HST, but HST is actually a small telescope. It's only 2 meters in diameter, and it doesn't work very well in the infrared. So that's why, in fact, it's these telescopes which really have done the most important work. I mentioned already VLBI, the radio technique, but also millimeter interferometry, X-rays, and even gamma rays have been used to look at these massive black holes. So in this sense, the problem of massive black holes has been attacked by all the big guns of modern astrophysics, and really it was definitely needed. Now, the first evidence, in fact, that there might indeed be mass surrounding this radio source, here again this radio image, you see there's this compact source, Sagittarius A star, then there is this sort of streams of ionized gas, which in fact you might sort of picture as gas orbiting in this central region, and then this very dense star cluster. All of this was first measured in the early 1970s. Some of the heroes of the early days, Eric Becklin, Ballack and Brown, who discovered Sagittarius A star. And then, in particular, Charlie Towns, Nobel laureate for the invention of the maser and the laser, who I should say is still alive. In fact, earlier this week, celebrated his 99th birthday. Pretty impressive. He's still... and Mark Morris started with the Keck telescopes on Mauna Kea. And the idea was basically, as I said, basically you try to measure the motions of stars. Here you see one of these adaptive optics images in the infrared. The radio source is where the cross is here. And you see there's some very bright stars. So we were hoping basically to make these sharp images on 1 year and another year and a third year, and just wait and be patient. And we had calculated that it would take us, if there was a few million solar mass object here, it would take us a few years until we would see actual motion. And we did. And so in the first experiment, The first stage of the experiment, to see the motions, I visualize here by basically zooming into the central light month. That's a light month here. That's what a radio source is, Sagittarius A star. And then you see three colored images in red, in green, and in blue. These are year 1, year 2, and year 3 in this experiment. And I would hope you would agree with me. This star here obviously is moving quite a bit, actually. If you convert this into a motion, there's a little calibration up here. This motion is about 100 times as fast as the Earth around the Sun. And that is now on a scale of, light days. And you can do the same thing. You can do v squared r over g, where now v squared is much bigger, r is much smaller. Turns out the combination is a few million solar masses. So what you learn is that from this stage of the experiment, there's obviously a mass. Is it concentrated, you might ask? Well, if it were concentrated, then Kepler's laws should hold, right? And Kepler's laws tell you, again, the planets around the sun orbiting in circles or ellipses, and orbital motion goes like 1/square of distance from the sun. Okay, so they increase to the center. And indeed, qualitatively, you can see this here by looking at the innermost stars. They show a lot of motion here, faint stars also. As you go out, the prism effects get less and less, right? So the stars get whiter and whiter out here. And that's basically qualitatively Kepler's laws telling you that the mass is concentrated. Quantitatively, it looks like this. You plot as a function of distance from the radio source the mean velocity, and indeed, it follows a 1/square of r law with a mass of about 3 million solar masses. So by the end 90s, both groups had confirmed this, the Keck group and the ESO group, and so that looked as indeed very likely that could envision that there is a cluster of a few million neutron stars here. Not that it's easy to realize this, but in principle, there could be basically a cluster of very faint but massive stars, neutron stars, white dwarfs, or anything else. And they would look like this, very concentrated, but not much radiation. So the question was, how would you exclude that such other configurations might be present? Well, you have to measure yet closer, obviously, because if it's an extended cluster of astrophysical objects, well then, as you go inwards, the mass should then begin to decrease rather than stay constant. And another thing you should keep in mind is that when we plot this velocities here, this is a mean velocity. That is, we are taking several stars at the same radius and then basically average. Why do we do that? That's because to determine actually a mass, you need to have the three-dimensional radius. But here you can only measure the two-dimensional radius. The third coordinate, which is the coordinate along the line of sight, we don't have. Right? We don't have that. And so then you have to do an averaging process and then basically project, so to speak, into a model in order to say something about the mass. But it would be wonderful, wouldn't it be, to be able to measure the mass from this object here alone, because obviously it seems to be so close. If it were that close, then of course the distance there is less than a light day. Less than a light day. So that's much closer than the average of the stars. And so that might be a way. So another way to get at this distance is to see deviations from straight motion. That is, if these things truly are on orbits, at some point they will curve, right? They will curve, having to be on ellipses, more or less. So that was sort of the idea. And then we started making simulations. It turned out to make that measurement, it would likely take us several hundred years. So that was disappointing, right? Because even even the best funded and most patient observer would say, well, that's not going to work. All right, should we give up? Not, of course. Measure more precisely is the idea, first of all. And indeed, at that time, many of the technical things which I had described initially came into being. We had built fancy new spectrometers which would take advantage of the adaptive optics, etc., etc. So that both groups are set into motion technology, which allowed us to measure ever more precisely both the motions on the sky as well as the motions along the line of sight. And then the rest was luck, as always. Nature just gave us an object which we didn't have any right or whatever to expect, which had an orbit of 15 years. That is something you can measure. So here's that orbit. Of course, in retrospect of this year or last year, when we started the experiments, it was up here, about a tenth or so, or 2/10 of an arc second, away from Sagittarius A star. That's where the X marks the spot. And then it moved sort of downward. And then in 2002, it was on the other side. And I tell you, that was one of these moments when you didn't need a computer. In fact, I took, graph paper and a ruler and, this kind of stuff. And you could easily see, well, this was obviously consistent at that time already with an orbit, a highly elliptical orbit of eccentricity 0.9 almost, where the peri-distance from Sagittarius A star was 17 light hours. So that's about 3 times the radius of Neptune. So that's solar system scale. And while you don't see that here these motions are motions from year to year to year. The blue ones are from our group, and the red ones are from Andrea Guess's group. You can immediately see how well they agree, by the way. But here we saw the motion from month to month. And so the motion then near Peri was about 6,000 kilometers per second. So clearly, now you can go ahead, 5,000 squared times 15 light hours divided by gravitation constant. What do you think we found? 3 million solar masses. So clearly all of that mass, which we had been finding since the 1970s, must be all contained within a minutiae volume here. And so in the end, of course, you see this orbit here, which we've now assembled over more than one go-around, is a perfect replica of an ellipse, of a Kepler ellipse, right? So it fits a Kepler ellipse perfectly, and that means we can now mathematically, of course, infer from this the mass very accurately, where the main uncertainty is actually not the measurement uncertainty, but the distance, which we can also infer, by the way. And we can say something about any deviations from a point mass. And that is because if you had a situation, say, where there would be a point mass here and then a background of other objects surrounding this, then as this orbit dives into this extended configuration, it would see a change in the potential and thereby a deviation from the orbit from a Kepler ellipse. Since there is no deviation from a Kepler ellipse, we can constrain the amount of mass which is within this orbit. And that's less than a few % of the central potential, okay? So the statement, therefore, is there's an object here of about 4 million solar mass. The main change here, by the way, is the distance to the earlier numbers. So there's 4 million solar mass object, which is essentially all within this orbit here, or a fraction of this orbit at 15 light hours, which is equivalent to a density of 10 to the 17, 10 to the 19 solar masses per cubic parsec. I'll tell you what that actually means in terms of masses. And I should say we're not only looking at this one star, we're looking, and you see this in the little upper talk a little more about Sagittarius star. So this is the radio image again. So there is your, in this image, unresolved radio source in the center. And in fact, the dynamical center of that orbit is that point mass to within our measurement accuracy, which at this point, I should say, is about 500 micro arc seconds. So over all of these years, I have not told you about this. Of course, we've been working hard to make better measurements by about a factor of 1,000 over the experiment. And so we can measure now to 200 micro arc seconds. Well, 200 micro arc seconds, that's about a few meters on the moon, okay? few meters on the moon. So that's our measurement accuracy. And so we know that Sergei star is in fact coincident with the center of force of that orbit. Now the radio astronomers can also measure Sergei star and measure its size. And here what you see are the red points are the size measurement of Sergei star as a function of wavelength at which it is measured. So this is the classical centimeter radio range, and that's the millimeter range. And you see that the size changes with lambda squared essentially to shorter wavelengths, always getting smaller. And unfortunately, this has nothing to do with the galactic center. This has something to do with the fact that the radio waves pass through electrons in the Milky Way, and along the line of sight there's blurring, just like seeing in the atmosphere at radio waves. So you have to actually, unfortunately, remove this blurring, and then the green points tell you what is the true intrinsic size. Because of that blurring, actually, I should say, we don't yet have an image in the classical sense of a two-dimensional image. That is to come soon, but we have a size, and that size is spectacularly small. So at the shortest wavelength where VLBI is possible, that size is 37 micro-arc seconds. And that is about 4 times the size of the event horizon of a 4 million solar mass black hole. Remember, we have evidence there's 4 million solar masses. Let's assume it's a black hole. Then it would, GR would tell us that it has an event horizon. So this radio emission must come from just around the event horizon size. And the theorists, of course, know how it should really look like. So their prediction, it'll look a little bit like this. Because basically there's a black hole here. And then in this immediate vicinity of the black hole, gravity is so strong that even, of course, photons get, basically curved around the black hole. And so you get something one would call a shadow effect. So something where you have sort of a dark region centered on the black hole and then the bright region surrounding it, because the gas is probably moving, which is producing the radio emission. The Doppler effect, due to special relativity, makes it bright on one side and faint on the other. So that's the prediction due to the theory. We will see whether it holds up with real measurements. But that's how an image might look like if we get one. The second thing the radio astronomers can do is, like in our experiment, they can look for changes in position. They do this basically by referring the radio source relative to background quasars. There are some background quasars near in the vicinity of the galactic center, and so they register that. Of course, then, because we are moving around the galactic center, what you get to see a combination of the motion of the black hole in the reference frame of the galactic center plus our motion around the black hole. In fact, when you plot the motion as a function of distance perpendicular to the Milky Way plane, which is where you wouldn't expect to see much motion from us. There is the measurement points. This is 10 years here. And the scale is 1 milliarc second. So the motion is very small. If you convert that into a velocity, that turns out to be 2 kilometers per second, this motion here. And all of that actually is explainable by what we know about our motion, the solar motion in the Milky Way. So this limit here is a very powerful limit, 2 kilometers per second. Remember, the stars, which are right around there, are moving at thousands of kilometers per second. That immediately tells you, obviously, this object must be heavy, right? Because if you have a heavy object and a light object about the same energy, then of course, because energy is proportional to mass and velocity squared, when the energy is the same, a slow object must have much more mass. Okay. In fact, if you make a model of this limit here turns out into a lower limit of the mass of the radio source, which is about 10 to the 5 solar masses. So that's 10% or 5% of the dynamical mass, a limit, okay? If indeed one could measure more precisely, one would expect the black hole to slosh around here in the galactic center potential with about 200 meters per second. Okay, that's not yet measurable, but maybe in the future sometime. So the radio source obviously is qualitatively consistent with a very heavy mass, which it is apparently associated with. So then you can summarize this entire situation currently in the following way. Let's plot here ten to the 5 times the event horizon. And then in this coordinate here, density, where I mean by density now within a fiducial volume, which is the size of a cluster, say, or in the case of a black hole would be the event horizon size. And so the most dense clusters, star clusters we know, realized in astrophysics, are down the bottom right. And in the upper left, that's where a black hole resides in this kind of a plot. Now then, you could go ahead and you tell me your favorite idea, what it might be we're observing, and we could put it in here. So for instance, you could say, well, let's put in a cluster of neutron stars in here, and you plot it, and you say it has a certain size, you put it in here. That's fine, but as soon as you tell me that, I can tell you how long that cluster will live. Okay? There's, in each position here, where if it's a cluster of astrophysical objects, there's a well-defined calculable lifetime. That has to do with the fact that these objects, stars or whatever else, exchange energy. And over a time, basically, they transfer ever more angular momentum and energy amongst each other, such that at the end, most of the mass goes into the center, collapses to a black hole, presumably, and the angular momentum is being removed to infinity. So that means that any astrophysical object you invent, while you can place it here, it won't stay there. Yeah? Theoretically, it will move from here to there, and the only thing you can say is a lifetime. So anything above here has a lifetime less than 100,000 years. Okay. Now that you would call a violation of the Copernican principle, because the stars we're looking at are, a million or billions of years old, and so if a cluster which you have somehow fabricated only lives 100,000 years, that doesn't seem very likely. Okay, so that's with that I can show you what the measurements tell us. The measurements exclude everything to the right and to the bottom of this. So in fact, if you wanted to maintain your star cluster, it would live for about a few thousand years. So that seems absurd. So what's left over in GR is your black hole. So by exclusion in the galactic center, as long as you accept that GR is right, you can show that this object we have discovered there or measured must be a black hole. So that's the best proof we now have in astrophysics that massive black holes, in fact also any black hole, exists. Now of course you could say, well, wait a second, I don't think that GR is right. That you're allowed to say, because GR has not been tested on these scales, and so you can come up with all kinds of configurations, and people have. I don't want to go through them. They're all, in a sense of the consensus opinion of the relativity community, highly unlikely. A boson star, for instance, a configuration of Higgs bosons, say, all confined to a small volume, wouldn't be stable as soon as there is baryonic accretion. In fact, that's happening. So this object you could place there, but it won't stay there very long. And then you could have objects beyond standard GR, which you're certainly entitled to propose them, but the experimentalist job is, of course, to disprove or prove them. So that will be our future job. Now you could ask, do we have any evidence for this event horizon, which was obviously one of the features of a black hole? And in a sort of a basically exclusion principle, we do. So here's in fact the emission as a function of frequency or energy from Sagittarius star. These are these various colored points. So there's radio emission, millimeter emission, that's where it peaks. Then sometimes there's X-ray emission, a little bit of infrared. So that's the overall emission from Sagittarius star itself, from the radio source itself. So let's assume that's a black hole. No, let's not assume it's a black hole. Let's assume it's an object with few million solar masses, and GR is wrong, and it has a surface. But a surface which fits into the constraints of the radio measurements. Remember, that was 30 micro-arc seconds. So an object which is very small and has a surface. Now then, of course, we know there's radio emission, which we believe is due to basically hot electrons emitting synchrotron radiation, and there's accretion onto this black hole. We roughly know what that accretion might be. And so then you can calculate how much accretion you can tolerate and not see it emerge here as a bump in the infrared and optical. That's basically, if there weren't surface, then the material bumping into the surface gets heated up. And you can calculate that that temperature is a temperature of a few hundred degrees given the size and the amount of accretion. So that would show up as sort of what we would call an infrared UV bump here. And so the fact that we don't see such a bump at all can tell us something about the amount of accretion which we can tolerate. And that amount of accretion, in fact, is so low that it barely can account for this radiation here at 100% emission efficiency. So that seems very unlikely that you can do 100% emission efficiency. So in that sense, we can say there can't be a surface. But this is a weak argument. I would not bet my life on this. It's an argument which we can come up with at that time. I don't have time here in this talk to tell you about all the wonderful other things which we can now do in terms of astrophysics once we convince ourselves now that there's a black hole. For instance, our theoretical colleagues can tell you in excruciating detail what we should or should not expect. So for instance, one of the things they would tell you, well, once you have a massive black hole in any star cluster around it, you shouldn't expect any star formation around it, because basically star formation, right, happens by gravitational contraction of a diffuse cloud. That's at least how it happens in our Milky Way. And then basically you form a new star. Now in the galactic center, that cloud cannot easily collapse because you have the tidal forces from the black hole. They are enormous. So there is a limit here called the Roche limit of density below which you cannot form stars from gas. And in fact, that limit in the central light years is so high that none of the gas we see there is even close to that. So none of the gas can collapse to form stars. And so in that sense, with the kind of gas densities we usually see in galactic nuclei, there shouldn't be much star formation. Here is our image. And in fact, since we can pick spectra, we can assign spectral types to hundreds and hundreds of stars. There are some old stars, many thousands of old stars, but there are also about 200 young stars, massive stars, some of them as massive as 100 solar masses. They have formed in the last few million years. So these are heavy old stars, Wolf-Rayet stars. The galactic central region is the most active star-forming region in the entire Milky Way. Remarkable. Absolutely orthogonal to what you would have expected. And the explanation, which I only give here in passing, is that there is probably gas which came in and formed a disk, and we can see the remnant of the disk nowadays by the motion pattern of those stars, which basically show a circulatory motion. And that happened 4 million years ago or so. We can age date that. And at that time, so to speak, a thick disk of gas formed, and that cooled down over time until, in fact, it overcame the Roche limit, and then it formed stars. So that's the likely encounter. The next theoretical expectation is once you have a black hole, then the equilibrium configuration of the old long-lived stars is a power law. So there's basically peaking at the black hole. That's called a Bacall-Wolf cusp and was predicted in the 1970s. Now we can measure that in the galactic center by basically counting stars. And here are the old stars. That's the distance from the galactic center. Here's the surface density. And just look at the red ones. There is no cusp. There is a cusp, but it's in the young stars. But these stars, they are typically younger than 50 million years, so they couldn't be in equilibrium. So that's an extreme puzzle. The next prediction, and here theory does much better, is sometimes a binary is being shot right at the galactic center black hole, just sort of by chance. It comes in on what we call a lost cone orbit. So you have a bound binary system which starts off far away from the galactic center and now goes onto a radial orbit into the region near the galactic center. In the meantime, of course, the kinetic energy of this system increases all the time just because of the force from the black hole, such that as the object comes close to the big black hole, the kinetic energy per particle, per binary particle, is much, much greater than the binding energy of the binary. Now you get a three-particle interaction, the big black hole and this very fast binary, which can lead to a little bit of transfer of energy from one to the other. And that means that the one binary gets stuck and the other one gets shot out at thousands of kilometers per second. So this mechanism, called the Hill's mechanism, predicts that black holes act like slingshots, firing off fast stars into the halo. You laugh, but they've been discovered. They have been discovered in two senses. One, we now believe that the stars which we use to make our motion analysis are the ones which got stuck, and the hypervelocity stars are in fact now discovered out in the halo, and they're a similar type of stars. The final prediction, where in fact theory does very poorly, is on the luminosity of this black hole. Just like in the case of quasars, if you have accretion onto such a black hole, you convert it into heat, you should, produce a lot of energy. Now you shouldn't expect to see a quasar all the time, but even a little bit of accretion, given the amount of gas, should make the galactic center extremely luminous, and it isn't, by about a factor of 10 to the 6 to 10 to the 8. So our galactic center is underluminous compared to what you expect by at least 1 million. And this accretion, I should say, is actually expected to come from stars. So here, in fact, there's the black hole here, and the black stuff are the stars moving around it, and they eject winds, and these winds basically is the material which flows into the galactic center. And so that their rate should be large enough that if that material gets to the center, that it is much, much more luminous than what we observe. And so in fact, the amount of accretion we currently see near the event horizon is about 10 to the minus 8 solar masses per year. So that's a big puzzle. And the resolution of the puzzle for many people for a while was there's no black hole here. But now it's basically having to do with accretion and how basically material gets into black holes. And the problem really is angular momentum. As material gets into the central region, at some point it gets just circularized. It's just too much angular momentum. It stops, so to speak, at a radius. And that angular momentum is much too large for the gas to go into the hole, into the event horizon. So in fact, most of the a particular thing which came in and is coming in is right now at the center, which turns out to be gas. So I told you there's gas around here, but this is a particularly neat story because it tells us a lot about the immediate vicinity of this black hole. So what we discovered basically was another object which we saw on our images going in on an orbit was basically straight in. So the eccentricity was 0.97. So somebody aimed here very, very well. And that something which came in was dust and not a normal star as we usually monitor it. We saw it also in gas, so it was an ionized, dusty thing on an almost radial orbit. Right now it's here, so it's right at its minimum distance of 20 light hours. So that's almost as close as this star S2, which you also see depicted here. But the main point is, in addition to potentially a star, there could be a star which we don't basically see, there is gas, about 3 to 10 Earth masses. And what we see is wonderful, wonderful detail of a tidal disruption. And I'll show you this now in this summary here. So the data are plotted in the top. And what you see here in vertical axis is radial velocity of this gas. And then in the bottom its position along the orbit of the gas. And then you did different time slots. So here's 2004, no, 8, 10, 11, 12, 13, 14. So that's this year. And so note what you see here. So in the early days, when we first discovered it, it's sort of a bright knot in space and velocity, a bright single knot. Forget about the tail here, just look at the bright stuff. Then, 1 year later or 2 years later, the little bright spot had moved on along an orbit, which is described by a highly elliptical orbit, but it got stretched a little bit. A year later, it got yet higher velocity. It got stretched more, and then it started all of a sudden to be also on the other side of the orbit, which is the blue side. Okay, so in 2014, it basically, half of them, of the head, what we call the head, is on the original side. The other half is on the other side. So this thing is now, a spaghetti, 10 times as long as it's wide, okay, and 20 light hours away from the black hole. And so why is that of excitement? Well, of course, we know that there's a black hole there. That's fine. We're not surprised about that. But gas sees not only gravity from the black hole, it also sees distributed stuff around the black hole. And we would expect there to be distributed stuff because that's the accretion. That's the thin, hot gas which is raining onto the black hole all the time. And so this gas cloud, in a way, is a perfect probe of looking how much gas there is and how it's distributed and so forth. So by basically looking at the dynamics of this cloud, we can say something about how much gas there is, other than the motion, the mass of the black hole. Now the bottom diagram here is a theoretical calculation where you start off with a artificial little cloud, which has to give it a little bit of a velocity spread initially, make it very compact, and let it go on this orbit. And you see, there's the head. Looks like that one, and then it starts stretching, and then it comes out on the other side. Turns out that this simulation here, which has in it only the tidal stretching due to just the forces of gravity, does a perfect job in mimicking our little cloud. So that means there is not much stuff there. Because if there were a lot of stuff, then we should see deviations of this gas here as it comes into the inner region from this orbit, which we see from the Keplerian orbit. So we don't see that. And so, very exciting thing. Another prediction here is from the simulation, which you see here. That's a two-dimensional full hydro simulation by Mark Schartmann and others. So you see a little cloud. Here you see it blow up. You see it gets hot at its leading edge. That's a bow shock as the plunges into the central region. Then it gets stretched, of course. That's the tidal stretching. And then it, as you see, gets smushed up. And in the end, it sort of overshoots, and then it comes back in. So that's the general prediction. And this stretching is just due to the tidal stretching. If there weren't any gas there, then as it came out, it would, so to speak, go back together more or less into a compact cloud. But the fact that it starts, getting disrupted here is due to the interaction in the simulation of this gas cloud with the hot stuff. So the prediction is that the cloud should get hot. You might expect it to emit X-rays, radio emission, etc. And be tidally disrupted, but so far no interaction with the medium. So what is the origin? Well, it could be a gas cloud by itself if it formed recently from some kind of an instability or part of a stream or something like this. Most people have favored the fact that actually what we're seeing is the outer parts of a star, maybe because it has a disk or because it has a wind. We feel that this is highly favored explanation now, because we don't see much of an increase in the radiation. Now, very recently, we've seen in our early images, not images, but spectra, I should say, that in addition to the thing I explained to you, this compact thing, there's this tail. So there's more to the cloud than just this head. And then there is also, in the early years, some amount of emission, which you wouldn't necessarily believe if you take that only as the only evidence, certain amount of emission on the other side of the orbit already 12 years ago. In fact, during the same time, there was also a dusty object near Sagittarius star. And we can plot out this dusty object and assume that this is seen here as blue here in space and in velocity. And the objects of this dust cloud, which I described to you in red. And then you see all of a sudden they are sort of more or less on the same orbit, with one exception. This orbit requires a slowing down, very substantial slowing down and circularization. So maybe, in fact, what we are seeing here is sort of a streamer of gas, where sometimes you form these little cloudlets, which then get disrupted, and then on the other side they get sort of basically circularized as expected because of the interaction with this hot gas. We'll see how that develops. But it's a fascinating story because maybe we've seen already the future already of that cloud. The fascination here, of course, in addition to just giving us information about the region around the black hole, is that we can make these measurements online. We can see these changes online. So let me finish here by telling you what we expect to do in the future with 2 slides. So as I said, I indicated already in the beginning, we are hoping to use the black hole now to play with it in the sense of general relativity, to test general relativity. The several experiments are underway. This one here is called gravity, where we basically take the 4 8-meter class telescopes of the ESO VLT. We've been using this one so far. Now we are basically combining the light of the 4 telescopes coherently. There's a tunnel underneath here, which is installed since some time. And so we are combining the light coherently to synthesize an optical telescope of 150 meter diameters. And that should give us resolution in terms of astrometric precision of 10 microarcseconds. So that's a cent coin on the moon, okay? It is also the size of the event horizon of the black hole. So if you make measurements on that scale, then we can hope to basically see in detail what general relativity will do. The radio astronomers are getting going on an experiment they call the Event Horizon Telescope to see the shadow, which I already mentioned to you. Then, hopefully in 10 years, the Europeans and the Americans and the rest of the world will have still bigger telescopes in various forms. Here's the 30-meter telescope here from California. This is the European version. We will see what we can get financed. It's not so clear that this has been it's a good idea. We think we can build it, but it's all very, very expensive. But once you have them, you could obviously make superb measurement with a higher resolution of these telescopes. And finally, the X-ray community will want to use spectroscopy and time-resolved spectroscopy to resolve motion. So there are several experiments in the near future. Gravity is being put together in the laboratory right now, and we hope to start commissioning the instrument next year. The VLBI experiment also should start next year. So within a few years, I hope we will have progress. So definitely, we think we can see deviations from Newton. So here's our S2 orbit in 2 coordinates in green, up to subtraction of the Keplerian orbit. And so GR should give this blue stuff. Okay, and so we are fairly certain that the next time the star will come around to Peri, which is in May 2018, please put it in your calendar, we should see these strong deviations. And that would be post-Newtonian effects like a gravitational redshift, longitudinal Doppler, and so forth. So that's pretty nice, but maybe not yet fully exciting. So the next stages would be the so-called Schwarzschild term of relativistic precession. For that, we probably need a star which is inside of the S2 orbit. If there is one, we have good hope, but we don't know. Still further in, there is the spin effects, the lens-tearing precession in particular, which one might hope to see. And then finally, in here, there's all kinds of fantastically exciting stuff having to do with testing, true basic fundamentals of the theory, like the so-called no-hair theorem, and perhaps even quantum effects, which are being speculated about currently. I would say I don't expect in my lifetime to get very far on this ladder, but what I hope I get across is we are actually going that route now. And the chances are that 1 or 2 steps can be done in the next decade. Of course, gravitational waves and investing them in a, say, black hole merger would be the ultimate way of doing this. So that's 50 years from now, maybe, or 40 years from now. These things may come in gradually over the next tens of years. So black holes, we now think we have good, compelling evidence, at least within the theory of general relativity. We are ready to test the theory on these kinds of scales. And of course, a story I have not told you about is the evolution of these black holes and how much they apparently, in fact, did have a role in shaping the evolution of our Milky Way as is of a general system. Well, thank you for coming.
Around the black hole. Are they in the plane of the galaxy? Are they at random?
Yeah, so, okay, this is part of the story I didn't. In fact, you saw it just now. Maybe we go backtrack here on the right. See, so now you see these are the orbits, and the innermost stars here, they're as random in terms of orientation as you could think. This is S2, the one we've talked about a lot. As random, basically a thermal distribution, slightly even super thermal, but all inclinations, all angular momenta, all eccentricities. Then you go further out, and then you begin to see this disk of stars due to this, very massive stars which formed about 4 million years ago. But the innermost region is completely random. And as I said, the most likely current explanation is this binary phenomenon where basically binaries get shot at the galactic center and they get stuck, right, and shot out.
So recently, Stephen Hawking kind of said that there is no such thing, he doesn't think, as an event horizon. And I was wondering if the experiment is going to be able to test his theory, or if you're...
there has been, as you probably know, a very intense discussion about the survival or not of information going into black holes. And the quantum community in general seems to now, I would say with strong majority, in fact persuading Hawking, who was on the other side, believe that quantum numbers have to be conserved, therefore they are located on, basically a hologram, so to speak, or the event horizon, or in the Hawking radiation. And so then you can discuss this and see that this can lead to inconsistencies between the classical GR expectation that if you're a sturdy astronaut and you fly through the event horizon, in your frame you won't see anything. It's just happy going, so to speak, until you end shortly thereafter in your frame in the singularity when happiness ends. But the quantum, one of the quantum discussions, so to speak, is no, that cannot be. There must be, in fact, an effect to be seen. That's the firewall. Okay, and so then Hawking is trying to, come up with a solution without a firewall. This is such a bubbly, interesting, but I would say uncertain discussion at this point. I wouldn't know what the answer is. There are very clever people working on this. I don't think we have a chance of testing this. this. Absolutely not, because from a theory point of view, this effects which we're discussing would happen in an object which is, at the end stage of its evaporation in terms of Hawking radiation. So this is not a big, massive astrophysical black hole.
First, let me thank you for this wonderful presentation. It seems to me, if you take into account the extraordinary importance of the result and the certainty with which it's been established, it's the greatest discovery of modern astronomy. But my question is, you mentioned a little bit about X-rays. Isn't there some interesting information from the flaring in X-rays that Chandra found and so on, variability in X-rays?
Yeah, right. So in fact, I did mention it, okay? So what is known as reverberation techniques. So if you have a situation where you have, say, in the simplest form, a disk of hot gas orbiting this black hole, and then you shine hard continuum X-rays on it, then you get, of course, a reflection of this radiation, which you can see in line emission, and you encode the motion in the line velocities. Okay, so that's seen, in fact, in a number of these black hole candidates. You see line broadening to several thousands of kilometers per second, shifts due to relativity, etc., etc. So when that was established, the hope was very strong 10 years ago, that you could now use the fact that the continuum radiation shining on this disk, so to speak, since it's varying, could be used to basically time resolve all of this, and thereby look, so to speak, in different regions. This reverberation technique would be wonderful, because then you could, in fact, ask the question, is there gas inside of the last stable orbit? All of these very fundamental issues. The problem is that the sort of the exciting source, the radiation, the continuum radiation, is not a point source. And it's not even clear where it's located. It's probably located above the black hole in sort of a hot corona. And the signature of this reverberation, which is sort of a variation of the responding line emission, has been very hard to see. A little bit is seen, but not easy to decipher. So that means that at least in the current situation with the current telescopes, either Chandra or XMM, the signal-noise ratio and the quality of the interpretation is not there. So the effect is too dirty, with other words. Effect is too dirty. The next generation telescope, Athena, might have that quality, certainly more signal-noise ratio to do it. But unfortunately, I think, as in many of these things, astronomy is not a physics experiment. If you get one like the cosmic microwave background, you better be grateful. But I mean, often enough, there's a lot of dirt involved.
Hi, I have a question here. I was just wondering what kinds of stars are orbiting this black hole and Sagittarius A, and that sort of leads up to the question is, could some of these stars have turned into pulsars, which would give you an ultimate test?
Absolutely, yeah. The pulsar story is one which ought to be given here, but you see I ran out of time as well. So the stars which we're delighted to have, and which shouldn't be there, are B stars.
Okay.
We see also a few A stars.
Oh, those are big hot stars, though.
These are big hot stars, and so they are short-lived, and that's why they cannot sort of be migrated into the central region. Therefore, this Hill's mechanism. There are a few late-type stars, but they are really the minority. So the cusp, these orbits in all directions and so forth, that's largely B stars and some A stars. Yet, of course, some of them might then turn into neutron stars, absolutely. And the expectation from our entire theory community is that the central light year should have somewhere between 100 and 500 neutron stars. And heck, amongst those, there should be pulsars. Right. And once you have a pulsar, because of the exquisite measurement precision of the radio astronomy, they don't have to have one at 15 light hours.
Yeah, then you can do a Russell-Hulse type of measurement.
Right, so, okay, well, you probably know, and certainly I can tell you, since I was a student, there have been 5 generations of radio experiments, ever improving on different telescopes of the generation, trying to see any pulsar. It all failed until 1 year ago, when in fact the X-ray astronomy community wanted to see G2, So they observed much more than they usually get, the galactic center, and they saw a magnetar, which is a pulsar.
Yes.
Unfortunately, not one which you can use for dynamics.
Too bad.
But at least that one told us very important thing. There had been the belief the reason nothing was seen for 40 years is basically because the amount of dispersion due to the electrons was so large that you couldn't see pulses. But that was not the case in the magnetar. The magnetar was actually relatively low dispersion. So that points in the direction that there are not that many neutron stars, or at least not pulsars. And there's an ongoing beginning discussion amongst the theorists what that might mean. Whether in the environment of the galactic center you might not form pulsars, or whether they might not migrate in there. There could be effects like, basically the more massive systems like stellar black holes pushing the neutron stars out. But it's absolutely, there's several radio groups right now who are still working very hard to see, because if they get one, that would be fantastic, yes.
All right. So, Reinhard, I encourage you, if you have any more questions, you can come up and chat to Reinhard afterwards. We have a special SETI.org talks mug. It's not quite a black hole, although it's black and has a hole.
It's pretty black.
That's all we can do for you today. Please join me in thanking Reinhard for his great